Learning outcome 9.8. Given x of t and h of t, calculate y of t and y of s using Laplace transforms. Given x of t and y of t, calculate h of t and h of s using Laplace transforms. Given h of t and y of t, calculate x of t and x of s using Laplace transforms. This should sound very familiar. You had a learning outcome in Chapter 4 that was very similar, but it was based on Fourier transforms. And learning outcome 9.1 discussed how Fourier transforms and Laplace transforms are related. Therefore, most of what you learned in learning outcome 4.7 applies directly here. But there are a couple of twists, so please stay tuned. Given an input signal x of t that's passed through a system h of t, the output is the convolution of x of t and h of t. In the Laplace domain, that means that our input is x of s, our system is h of s, and y of s will be x of s times h of s. You see this property in Table 10.1. We're going to use this such that if we know two of these items, we can find the third. So let's say we know x of t and h of t and want to find y of t. We will take these two functions, convert them to Laplace. From there, determine the Laplace function y of s, and from there, we will determine our y of t. Likewise, if we know y of t and h of t, we will use those to calculate the Laplace transforms of those two, and from those determine x of s, and from x of s determine x of t. In the final case, we know y of t and x of t. We use them to find y of s and x of s. Those we combine to find h of s, and from h of s we find h of t. Just like you did with Fourier transforms. So let's work through a couple examples. The first three will look very similar to Fourier transforms and the video on that topic. The fourth one, however, is new material. In this example, you're given x of t and h of t. The next step is to determine x of s and h of s. But what's new is you also need to determine the region of convergence that goes with that x of s and that h of s. And for h of s, it has two terms. Therefore, it has two regions of convergence. We need to find their intersection. Real of s greater than -1 and real of s greater than -2 intersect at real of s greater than -1. Our y of s is determined based on x of s and h of s. And therefore, we need the ROC from x of s and the ROC from our h of s. We need to find that intersection, which will be real of s greater than -1. And this is the ROC that will go with y of s. We now do partial fractions, just like we did with Fourier transforms. The trick is that now as we do the inversion, we need to look at this ROC, because each of these terms have two possible inverses. And you need to see which of those two is satisfied with this ROC. And therefore, you can pick the correct inverse. Example 2. You're given h of t and y of t. We again determine their Laplace transform, but this time again we need to find the regions of convergence that go with this transform. For this function, we have real of s greater than -2 and real of s greater than -1. The intersection of that is real of s greater than -1. For this y of t, the Laplace transform, and again, the ROCs that go with it. Find their intersection, and now we can proceed. We know that y of s is a product of x of s and h of s. Therefore, x of s will be y of s divided by h of s. We can take our y of s function, divide by our h of s function, do some algebra, and we now need to take the ROCs that we are given for h and for y, combine them. In this case, it's trivial. And as we go to do the inverse of this Laplace transform, we need to use this to decide which one of those inverses we will use. Third example. You're given x of t and y of t. We find their Laplace transforms, determine h of s, and then h of t. Laplace transform for x of t, remember to find the ROC. Laplace transform for y of t, again, remember to find the ROC for each term. We need to find the intersection of those. Y of s is a product of x of s and h of s. Therefore, h of s is y of s divided by x of s. Substitute in our functions, do some algebra, and now look at the ROC for the y and the ROC for the x. Find their intersection. Do partial fractions, and for each term, as you're deciding on the inverse transform, use this ROC to help you make the decision as to which inverse you use. Last example, and this is where the equations look the same, but we're really going to use that ROC information. Same procedure. You're given x, you're given h, find the Laplace transforms. Given x, that's our Laplace transform and the ROC that goes with it. Given h, here's the Laplace transform. Notice that this one is different. It has u of -t. So we negate the sign here, and our region of convergence for this term will be less than -1 instead of greater than -1. Find the intersection of these two. Take the product of these two terms. And y of s is now the product of x and h. Take our x, take our h, and we need to take the ROC for our x and for our h, and find that intersection. Now we do partial fractions, and for each of these, we need to look at the ROC and decide which ROC corresponds to the correct inverse. These two correspond to this part of the ROC, and this is controlled by this part of the ROC. This result will contain this ROC. Notice again the -t in our unit step function, and how this negative sign went away in the inverse transform. This problem is very different than anything you've seen before. Think through it again. Draw pictures of those ROCs. This is new stuff. It looks just like the old stuff, but if you don't understand the ROCs, it's very easy for you to make a mistake. Ask me if you have questions.